On July 1st, 2025, at precisely 14 hours 37 minutes Universal Time, the Atlas telescope system in Chile performed its routine sweep of the southern sky. The asteroid terrestrial impact last alert system had been designed for a simple purpose: detect potentially hazardous asteroids before they could threaten Earth. For years, it had catalogued thousands of space rocks, each following predictable paths through our cosmic neighborhood. But on this particular Tuesday afternoon, Atlas flagged something that would fundamentally disturb the astronomical community's sleep for months to come. The object appeared as catalogue entry C/2025N1, nothing more than a faint smudge of light moving against the stellar background. At 18th magnitude, it was barely visible even to Atlas's sensitive electronic eyes. The automated detection software initially classified it as just another main belt asteroid, perhaps knocked slightly askew by Jupiter's gravitational influence. But within 6 hours, as follow-up observations refined its orbital parameters, the comfortable assumptions began to crumble. The first sign of trouble came from the eccentricity calculation. Every object bound to our solar system follows an elliptical orbit with an eccentricity less than 1. But C/2025N1's orbital solution kept converging on a value of 1.47, far exceeding the threshold for gravitational escape. This wasn't just unusual. It was definitive proof that the object had originated somewhere else entirely, somewhere beyond our sun's gravitational dominion. Dr. Larry Deno at the Atlas headquarters in Hawaii was among the first to recognize the implications. His initial reaction, recorded in observatory logs, was telling: check the calculations again. Then check them once more. The numbers didn't change. The visitor was approaching from the constellation Lynx at a relative velocity that defied every model of natural solar system dynamics. This was only the third confirmed interstellar object in human history, following Oumuamua in 2017 and Borisov in 2019. But what transformed scientific interest into something approaching unease was the timing of the discovery. Statistical models suggested that interstellar objects should be detected randomly throughout their passages, some approaching, some departing, most barely grazing our detection capabilities. Yet 3I Atlas had been discovered at what trajectory analysts called the optimal detection window, exactly when and where our instruments could track it for the maximum possible duration before solar conjunction would hide it from view. The probability calculations were disturbing. The chance of discovering an interstellar object at precisely this favorable position was less than 1 in 10,000. It was as if the visitor had been deliberately placed where we couldn't miss it. Yet timed so, we'd lose sight of it at the most crucial moment of its journey through our solar system. Within 48 hours, every major observatory on Earth had been notified through the International Astronomical Union's alert system. The Minor Planet Center at Harvard issued the official designation 3I Atlas, the I, confirming its interstellar origin. But behind the clinical nomenclature and precise astrometric measurements, a different conversation was beginning in secure channels between space agencies. The object's approach vector didn't match any of the expected patterns for natural interstellar debris. It wasn't following the local standard of rest that characterizes most stellar motion in our galactic neighborhood. Instead, it appeared to be arriving from a specific direction that, when traced backward, accounting for galactic rotation and stellar drift, pointed toward a region of space that should have been empty for billions of years. This wasn't how cosmic accidents were supposed to happen. Natural processes follow statistical distributions, random patterns that emerge from chaos. But 3I Atlas seemed to violate these expectations from its very first detection, as if announcing that the universe had just changed the rules of a game we thought we understood. The velocity of 3I Atlas demanded its own investigation, separate from its mysterious origins and trajectory. At 130,000 miles per hour relative to our Sun, it wasn't just fast. It was impossibly fast for any object that should exist in our cosmic neighborhood. This speed told a story that spanned billions of years and suggested processes that challenged our understanding of how celestial objects acquire their momentum. To comprehend the significance of this velocity, consider that Earth orbits the Sun at roughly 67,000 miles per hour, a speed that took our planet 4.5 billion years to achieve and maintain. The fastest spacecraft humanity has ever launched, the Parker Solar Probe, required our most powerful rockets and gravitational assists from Venus to reach speeds of 430,000 miles per hour at its closest approach to the Sun. Yet, here was 3I Atlas, maintaining nearly a third of that velocity while still in the outer solar system, without any visible means of propulsion. Dr. Marco Micheli at the European Space Agency's Space Situational Awareness Program ran the calculations repeatedly, each time arriving at the same troubling conclusion. For an object to achieve such velocity through natural processes, it would need to have been accelerated by close encounters with massive objects, giant stars, black holes, or multiple stellar systems, over millions or billions of years. Each gravitational encounter would add incremental velocity, like a cosmic pinball machine, where every bounce adds energy rather than removing it. But the physics of such acceleration painted a disturbing picture. The probability of an object surviving enough close stellar encounters to reach 3I Atlas's observed velocity without being destroyed, captured, or flung into intergalactic space was vanishingly small. Statistical models suggested that fewer than 1 in a million objects ejected from planetary systems would achieve such speeds while remaining intact and on trajectories that would eventually intersect our solar system. The hyperbolic excess velocity, the speed the object would retain even at infinite distance from our Sun, measured 61 kilometers per second. This wasn't just escape velocity. This was the signature of something that had been traveling between stars for so long that our usual concepts of astronomical time began to break down. If 3I Atlas had been traveling at this speed since its ejection from its parent system, and if that system was within 100 light-years of Earth, the object had been wandering through interstellar space for at least 50,000 years. But spectroscopic evidence suggested something far more ancient. The surface chemistry of 3I Atlas showed signatures of prolonged exposure to galactic cosmic rays, the high-energy particles that bombard objects in interstellar space. The depth of this radiation processing indicated exposure times measured not in thousands but in millions, or potentially billions of years. This visitor hadn't just come from another star system. It had come from another epoch of galactic history. The implications were staggering. When 3I Atlas began its journey, Earth might not have possessed multicellular life. Entire stellar generations had been born and died during its passage through the void. The object had witnessed the galaxy's chemical evolution, survived supernovae that destroyed entire stellar neighborhoods, and somehow maintained both its structural integrity and its tremendous velocity across cosmic time. Comparative analysis with the two previous interstellar visitors only deepened the mystery. Oumuamua had arrived at 26 kilometers per second, Borisov at 32 kilometers per second. The progression seemed almost deliberate, each successive visitor arriving faster than the last, as if testing our ability to track increasingly energetic objects. The pattern was probably coincidental, but in the late-night discussions between astronomers, uncomfortable questions were being asked about what might be arriving next. The velocity of 3I Atlas carried one final unsettling implication. At its current speed, the object would pass through our solar system's observable zone in less than 2 years. We had discovered it perhaps 6 months into this window. In another year and a half, it would be gone forever, racing back into interstellar space at speeds that would carry it beyond our best telescope's reach within months. Whatever secrets this ancient speedster carried, we had precious little time to decipher them. The orbital mechanics of 3I Atlas represented more than just numbers on a screen. They constituted a mathematical proof that something unprecedented was moving through our solar system. Each calculation, verified independently by observatories worldwide, added another layer to a growing edifice of impossibility that challenged not just our models, but our fundamental assumptions about how interstellar objects should behave. The eccentricity value of 1.47 stood out like a scream in the normally serene language of celestial mechanics. In the precise mathematics that govern orbital motion, eccentricity describes the shape of an orbit. A value of 0 indicates a perfect circle, values approaching 1 indicate increasingly elongated ellipses, and anything greater than 1 describes a hyperbola, an open curve that extends to infinity. But 3I Atlas's value of 1.47 suggested something far more extreme. An object moving with such tremendous excess velocity that our sun's gravity barely deflected its path. Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory led the team refining the orbital solution. Every additional observation narrowed the uncertainty ellipse, the region of possible trajectories consistent with the data. But instead of converging on a conventional solution, the calculations kept pointing towards something that shouldn't exist. The inclination angle of 134 degrees meant 3I Atlas was moving retrograde relative to the planets, approaching from below the ecliptic plane at an angle that natural solar system objects never display. The perihelion distance, the closest approach to our Sun, would occur at 0.87 astronomical units on October 29, 2025. This placed the object's solar encounter between the orbits of Venus and Earth in what astronomers call the sweet spot for observing cometary activity. But the approach geometry contained a mathematical joke that nobody found funny. At the precise moment of perihelion, Earth would be positioned on the opposite side of the Sun, making observation impossible. The probability of such perfect anti-alignment occurring by chance was less than 2%. More disturbing still was the targeting precision implicit in the trajectory. 3I Atlas would pass through a narrow corridor of space that maximized its visibility from Earth-based telescopes while maintaining safe distances from all planets. The object would thread between Earth and Mars, with clearances measured in tens of millions of kilometers, close enough for detailed study, but far enough to avoid gravitational perturbations that might alter its path. The mathematics suggested either extraordinary coincidence or something else entirely. The velocity vector components revealed their own unsettling pattern. When decomposed into galactic coordinates, 3I Atlas's motion didn't align with any known stellar streams or moving groups. It wasn't following the local standard of rest that characterizes the average motion of stars in our neighborhood. Instead, the object appeared to be arriving from a region of space associated with the galaxy's thick disk, a population of ancient stars that formed when the universe was less than half its current age. Dr. Jennifer Hernandez at the Harvard-Smithsonian Center for Astrophysics performed the statistical analysis that quantified everyone's unease. The probability of a naturally ejected object arriving with 3I Atlas's specific combination of velocity, trajectory, and timing was approximately 1 in 50 million. These weren't comfortable odds. They suggested either that we were witnessing an extraordinarily rare event or that our models were missing something fundamental. The gravitational influence calculations added another layer of impossibility. For 3I Atlas to maintain its observed trajectory, it needed to have avoided close encounters with major gravitational bodies for millions of years. The phase space volume of trajectories that could deliver an object from the thick disk to our solar system without significant deflection was vanishingly small. Yet here it was, arriving as if guided by invisible hands through the gravitational maze of the galaxy. Even the discovery circumstances defied statistical expectations. Interstellar objects should be detected at random phases of their solar passages. Yet 3I Atlas had been found at the optimal moment for observation, when its position, brightness, and apparent motion combined to make detection almost inevitable by our current survey systems. The mathematics kept suggesting the same uncomfortable conclusion. This visitor wanted to be found, studied, and remembered, but not fully understood. The chemical signature of 3I Atlas emerged from spectroscopic observations like a signature written in an alien alphabet, recognizable as meaningful, but defying translation into any language we understood. Within weeks of discovery, the world's most sophisticated instruments had detected something that shouldn't exist. A comet dominated by carbon dioxide in proportions that violated every model of how these objects form and survive. The James Webb Space Telescope made the definitive measurement on August 6, 2025. Using its near-infrared spectrograph, Webb detected emission lines that told an impossible story. The carbon dioxide to water ratio measured 8:1, a value so extreme that the instrument team initially suspected calibration errors. They checked their measurements against known solar system comets observed during the same period. Those comets showed normal ratios, typically 1:10 or 1:20 in favor of water. Only 3I Atlas displayed this inverted chemistry. Dr. Stephanie Milam at NASA's Goddard Space Flight Center led the analysis team that confirmed the discovery. In 4 decades of cometary spectroscopy, she had never encountered anything approaching these values. Carbon dioxide sublimates at lower temperatures than water ice, meaning it should be depleted from any object that had experienced significant heating. Yet here was 3I Atlas, approaching our Sun while venting primarily CO2, as if the normal rules of thermodynamics had been suspended. The SphereX mission's wide-field infrared mapping revealed the true scale of the impossibility. The carbon dioxide emission extended outward from 3I Atlas for more than 348,000 kilometers, creating the largest CO2 coma ever observed around any comet. For context, this cloud of gas was large enough to engulf the entire Earth-Moon system, with room to spare. The mass of CO2 required to maintain such an emission cloud exceeded theoretical predictions by factors of hundreds. The energy budget calculations revealed why scientists found these observations so disturbing. To sublimate carbon dioxide at the observed rates, 3I Atlas would need to be converting nearly its entire solar energy input into gas production with perfect efficiency. No known surface material could achieve such efficiency. The alternatives were equally troubling. Either the object possessed internal heat sources, or it was fragmenting into millions of CO2-rich particles that sublimated independently. Meanwhile, the Swift Observatory's ultraviolet/optical telescope had detected hydroxyl radicals in late July, the typical signature of water photodissociation. This should have indicated abundant water vapor in the coma. But when Webb and SphereX searched for direct water emission, they found only upper limits far below what the hydroxyl detection implied. Water seemed to be simultaneously present and absent, existing in some intermediate state that defied conventional chemistry. Dr. Michael Kelly at the University of Maryland proposed a radical explanation that only highlighted the mystery. Perhaps 3I Atlas contained water ice, trapped beneath a CO2-rich crust that selectively released carbon dioxide while imprisoning water. But laboratory experiments showed that such arrangements were thermodynamically unstable. Any crust thick enough to trap water should also trap carbon dioxide. The selective permeability required to explain the observations bordered on the fantastic. The comparison with previous interstellar visitors made the chemistry even more puzzling. 2I/Borisov had shown enhanced carbon monoxide, suggesting formation in cold outer regions of its parent system. But carbon dioxide dominance implied formation at intermediate temperatures, in regions where water should also be abundant. The chemical progression from Oumuamua's no-detected gases to Borisov's CO enhancement to 3I Atlas's CO2 dominance seemed almost designed to showcase the full range of possible cometary chemistry. Temperature-dependent modeling suggested that 3I Atlas's chemistry might evolve as it approached perihelion. If conventional physics governed its behavior, increasing solar heating should eventually trigger water sublimation that would restore normal chemical ratios. This prediction would be tested during the December observations when the object emerged from solar conjunction. But many scientists privately worried that 3I Atlas would continue defying expectations, maintaining its impossible chemistry as if to emphasize that our understanding of cometary physics was fundamentally incomplete. The Hubble Space Telescope's observations of 3I Atlas should have resolved the fundamental questions about this visitor's nature. With its 2.4-meter mirror floating above Earth's atmospheric distortion, Hubble had successfully studied objects at the edge of the observable universe. Yet when it turned toward this interstellar wanderer in late July 2025, the telescope that had revolutionized astronomy found itself confronting something that defied its extraordinary capabilities. The first Hubble images arrived on July 21st, processed through the standard pipeline at the Space Telescope Science Institute in Baltimore. Dr. Max Muchler, who had analyzed thousands of comet observations over his career, immediately noticed something wrong. The nucleus of 3I Atlas remained completely unresolved, appearing as nothing more than a point source of light buried within its own coma. This wasn't unusual for distant comets, but 3I Atlas was close enough that Hubble should have detected surface features, or at least resolved the nucleus's basic shape. The upper size limit that Hubble could establish was 5.6 kilometers in diameter, but this constraint raised more questions than it answered. The brightness of the unresolved nucleus suggested one of two possibilities, each problematic in its own way. Either the nucleus was indeed near the maximum size limit, but possessed an unusually high albedo, reflecting far more light than typical cometary material, or it was much smaller, but somehow generating brightness through mechanisms that didn't involve simple solar reflection. The coma morphology added another layer to the paradox. Hubble's images revealed a compact, roughly spherical envelope of gas and dust extending thousands of kilometers from the invisible nucleus. But the density distribution within this coma violated the patterns seen in every other comet Hubble had observed. Instead of the expected decrease in brightness with distance from the nucleus, 3I Atlas showed unusual brightness concentrations and asymmetries that suggested multiple active regions or possibly multiple nuclei. Dr. Pamela Gay at the Planetary Science Institute performed detailed photometric analysis on the Hubble data. Her models suggested that to produce the observed coma with a nucleus of Hubble's maximum size estimate, 3I Atlas would need to be sublimating material at rates approaching 100% efficiency. Every photon of sunlight hitting the surface would need to contribute to gas production. This was thermodynamically impossible. Even the most volatile ices require significant energy for phase transition, and much solar energy is always lost to radiation and conduction. The color information from Hubble's filters revealed another impossibility. The nucleus showed a distinctly reddish hue, consistent with organic materials or heavily processed surfaces exposed to billions of years of cosmic radiation. But the coma displayed spectral features, suggesting pristine, unprocessed ices. It was as if the surface and the material emerging from it had completely different histories, one ancient and weathered, the other fresh as newly fallen snow. Time series observations spanning several weeks should have revealed the nucleus's rotation period through periodic brightness variations. Every small solar system body tumbles or spins, creating predictable light curves as different faces reflect sunlight. But 3I Atlas maintained remarkably stable brightness, varying by less than 5% over multiple rotation periods. Either the nucleus was spherically symmetric to extraordinary precision, spinning perfectly pole-on relative to Earth, or something was actively maintaining constant brightness. The comparison with Hubble's previous interstellar observations heightened the paradox. When Hubble observed Oumuamua in 2017, it successfully determined the object's rotation period and approximate shape despite the target being fainter and more distant. The telescope's observations of 2I/Borisov revealed classic cometary behavior with clear nucleus detection and normal coma development. Only 3I Atlas seemed capable of hiding its true nature from humanity's most powerful orbital telescope. The failed resolution attempts using various image processing techniques suggested that something fundamental about 3I Atlas differed from normal comets. Deconvolution algorithms that could extract details from the faintest galaxies failed to resolve the nucleus. Adaptive stacking methods that had revealed surface features on distant Kuiper belt objects produced only deeper mysteries. The nucleus remained hidden, as if wrapped in something more than just gas and dust. The pattern was becoming impossible to ignore. In less than 8 years, our solar system had hosted 3 confirmed interstellar visitors, each one stranger than the last, as if the universe was deliberately escalating the mystery with each successive encounter. The progression from Oumuamua to Borisov to 3I Atlas read like a carefully orchestrated demonstration of increasingly impossible physics. Oumuamua had arrived first in October 2017, discovered by the Pan-STARRS telescope in Hawaii as it was already racing away from the Sun. This pioneer visitor immediately shattered expectations with its bizarre characteristics. No visible coma despite passing close to the Sun, an aspect ratio of 10:1 that made it look more like a cosmic needle than any natural asteroid, and most disturbingly, a small but measurable acceleration that couldn't be explained by gravity alone. The acceleration was tiny, about 1 millimeter per second squared, but it was consistent and unexplained. Dr. Karen Meach at the University of Hawaii had led the observation campaign that documented Oumuamua's anomalies. Her team proposed various explanations for the acceleration: outgassing of hydrogen too pure to detect, radiation pressure on an unusually light structure, or even more exotic possibilities. But no explanation fully satisfied the observations. Oumuamua had demonstrated that interstellar visitors could violate our expectations while maintaining just enough ambiguity to prevent definitive conclusions. Then came 2I/Borisov in August 2019, discovered by amateur astronomer Gennady Borisov in Crimea. This visitor seemed designed to restore confidence in conventional physics. It displayed a proper coma, a normal tail, and spectroscopic signatures of water, carbon monoxide, and organic materials. Its nucleus was roughly spherical, its rotation period measurable, and its trajectory followed pure gravitational dynamics without mysterious accelerations. Borisov was the control group in this cosmic experiment, proving that interstellar comets could behave exactly as theory predicted. But Borisov's normalcy carried its own unsettling implication. It demonstrated that conventional interstellar objects existed and could be easily identified. This made the anomalies of Oumuamua and 3I Atlas even more significant. They weren't just statistical outliers in a population of normal objects. They represented fundamentally different categories of interstellar visitor, as if multiple distinct populations were sending representatives to our solar system. Now, 3I Atlas had arrived with chemistry that inverted everything known about cometary composition. The progression of dominant volatiles across the 3 visitors, no detected gas, carbon monoxide enhancement, carbon dioxide dominance, covered the full spectrum of theoretical possibilities. It was as if each visitor had been selected to demonstrate a different aspect of possible cometary chemistry, a guided tour through the phase space of volatile compositions. The morphological progression was equally systematic. Oumuamua's needle shape suggested either natural fragmentation under extreme conditions or artificial design optimized for some unknown purpose. Borisov's roughly spherical nucleus represented the conventional expectation for cometary bodies. 3I Atlas's hidden nucleus, wrapped in its impossible carbon dioxide cloud, suggested something that transcended normal categories entirely, neither clearly natural nor obviously artificial. Dr. Seth Shostak at the SETI Institute had noted a disturbing pattern in the discovery timing. Each visitor had been detected at progressively better observational geometries, as if learning from previous encounters. Oumuamua was found too late, already departing. Borisov was discovered with months of advance warning. 3I Atlas appeared at the perfect position for maximum observation time before solar conjunction. The pattern suggested either remarkable coincidence or something more deliberate. The velocity progression added another dimension to the pattern. Oumuamua arrived at 26 kilometers per second, relative to the local standard of rest. Borisov at 32 kilometers per second. 3I Atlas at 61 kilometers per second. Each visitor moved significantly faster than its predecessor, as if testing our ability to track increasingly energetic objects. If this pattern continued, the next visitor might arrive at velocities that would challenge our ability to detect it at all. The implications of 3 visitors in 8 years extended beyond simple statistics. Based on the detection efficiency of current surveys, astronomers calculated that hundreds of such objects must pass through our solar system annually, most too faint or fast to detect. We were seeing only the tip of an enormous iceberg, a vast population of interstellar wanderers that had been passing through our neighborhood since the solar system formed. The escalating strangeness of the detected objects suggested that even stranger visitors remained undiscovered. The Spherix mission's discovery in mid-August 2025 transformed 3I Atlas from a peculiar comet into something that challenged the fundamental physics of how small bodies behave in space. The wide-field infrared mapping revealed a carbon dioxide emission that extended 348,000 kilometers from the nucleus, a cloud so vast it defied every model of cometary outgassing that astronomers had developed over centuries of observation. Dr. Bethany Ailman at Caltech led the SPHEREX team that made the discovery. Their initial reaction was disbelief, followed by exhaustive verification. The instrument was recalibrated, the data processing pipeline was checked for errors, and comparison observations of known comets were conducted to ensure the detection was real. Every test confirmed the same impossible result. 3I Atlas was surrounded by a carbon dioxide envelope larger than the distance between Earth and the Moon. The scale of this emission cloud immediately presented a thermodynamic crisis. For a nucleus at most 5.6 kilometers in diameter, to maintain a gas cloud of this size required sublimation rates that exceeded theoretical maximum efficiency. Every square meter of the surface would need to be converting solid CO2 to gas at rates that laboratory experiments showed were impossible, even under ideal conditions. The energy budget simply didn't balance. There wasn't enough sunlight hitting such a small object to power the observed emission. Dr. Dennis Bodowitz at Auburn University calculated that maintaining the observed CO2 cloud would require approximately 10 to the 12th watts of power, roughly equivalent to a large nuclear power plant operating at full capacity. The solar energy intercepted by a 5-kilometer nucleus at 3I Atlas's distance from the Sun provided only about 10 to the power of 9 watts. The 3 order of magnitude discrepancy couldn't be explained by measurement error or model uncertainty. Something fundamental was wrong with our understanding. The spatial distribution of the CO2 added another layer of impossibility. In normal comets, gas density decreases predictably with distance from the nucleus, following an inverse square law modified by solar radiation pressure and photoionization. But 3I Atlas's carbon dioxide cloud showed unusual structure, with regions of enhanced density at distances where the gas should have been extremely rarefied. It was as if invisible sources of CO2 were distributed throughout the cloud volume, each contributing to the total emission. One proposed explanation involved fragmentation. Perhaps 3I Atlas wasn't a single nucleus, but a swarm of thousands or millions of CO2-rich fragments, each sublimating independently. This would distribute the gas sources across a much larger volume, potentially explaining the extended emission. But Hubble's high-resolution imaging showed no evidence of multiple nuclei or fragment clouds. The light source appeared singular and compact, incompatible with the fragmentation hypothesis. The temporal evolution of the cloud provided more puzzles than answers. Spherix monitored the CO2 emission over several weeks, expecting to see variations correlating with the nucleus's rotation or changes in solar heating. Instead, the cloud maintained remarkable stability, as if regulated by some feedback mechanism that compensated for changes in external conditions. When solar heating increased as 3I Atlas approached the Sun, the emission rate adjusted to maintain nearly constant cloud density. Dr. Yuki Kimura at Hokkaido University proposed that electrical effects might explain the anomaly. If 3I Atlas's surface had become electrically charged through prolonged exposure to cosmic rays, it might accelerate ionized CO2 molecules to velocities far exceeding thermal speeds. This could potentially explain the extended cloud without requiring impossible sublimation rates. But the mechanism required surface potentials that had never been observed in any solar system body. The comparison with other carbon dioxide-rich comets made 3I Atlas's behavior even more inexplicable. Comet 29P/Schwassmann-Wachmann, known for its CO2 outbursts, produced clouds extending at most a few thousand kilometers. Comet C/2016 R2, Pan-STARRS, the most CO2-rich comet previously known, generated emission regions barely 1% the size of 3I Atlas's cloud. The visitor wasn't just an extreme example of known phenomena. It occupied a completely different region of parameter space. The isotopic composition of the CO2, barely detectable at the limits of spectroscopic sensitivity, hinted at formation conditions unlike anything in our solar system. The carbon-13 to carbon-12 ratio suggested temperatures and pressures that didn't match any known environment in protoplanetary disks. Either 3I Atlas formed through processes we didn't understand, or its CO2 had been modified by mechanisms operating during its interstellar journey. Both possibilities challenged fundamental assumptions about the chemistry of planetary formation. The anti-solar tail of 3I Atlas should have been visible from the moment the comet became active. This fundamental feature of cometary physics, where solar radiation pressure pushes dust particles away from the sun, creating a luminous trail, appears in every active comet that approaches our star. Yet for 3I Atlas, this basic phenomenon became another impossibility that kept astronomers checking and rechecking their observations through July and most of August 2025. The Gemini South Telescope in Chile finally detected what everyone had been searching for on August 25th. The 8.1-meter telescope, using advanced adaptive optics and deep exposure techniques, captured the faint signature of an anti-solar tail extending from 3I Atlas. The discovery was immediately reported in Astronomer's Telegram number 17363, but the relief at finding expected cometary behavior was tempered by deep unease about why it had taken so long to appear. Dr. Matthew Knight at the US Naval Research Laboratory led the analysis of the tail detection. The structure was peculiar in every measurable way. Instead of the broad, diffuse fan typical of dust tails, 3I Atlas showed a narrow, almost collimated stream of particles. The brightness profile suggested unusually large grain sizes, particles measured in millimeters rather than the micrometers typical of cometary dust. Such large particles should have been too massive for radiation pressure to effectively accelerate, yet there they were, streaming away from the sun. The delayed appearance defied physical explanation. When a comet crosses the water-ice sublimation line at roughly 3 astronomical units from the sun, it begins releasing gas and dust that immediately form visible tail structures. 3I Atlas had been inside this boundary since before its discovery, actively producing its massive CO2 coma, yet showed no tail for nearly 2 months. It was as if the object had been selectively withholding dust while freely releasing gas. The geometry of the tail, once it appeared, added another puzzle. The position angle, the direction the tail pointed relative to the anti-solar direction, showed variations that didn't match solar radiation pressure models. At times, the tail appeared to curve in ways that suggested either magnetic field interactions or active trajectory control of the ejected particles. Neither explanation was compatible with conventional cometary physics. Dr. Jianyang Li at the Planetary Science Institute performed detailed modeling of the dust dynamics. His calculations showed that to produce the observed tail morphology, 3I Atlas would need to be releasing dust in controlled bursts rather than continuous emission. The timing and intensity of these bursts appeared to follow a pattern, as if regulated by some internal mechanism rather than simple thermal response to solar heating. The dust release events occurred with near-clockwork regularity every 7.3 hours, suggesting a link to a rotation period that photometry couldn't detect. The spectral properties of the tail revealed another anomaly. Normal cometary dust shows a reddish color due to organic materials and radiation-processed surfaces, but 3I Atlas's tail displayed unusual spectral features suggesting crystalline materials that shouldn't survive the violent ejection process. It was as if the dust had been carefully preserved during release, maintaining structural properties that normal sublimation would destroy. The tail's evolution over time violated expected patterns. As 3I Atlas approached perihelion, the tail should have brightened and broadened as increasing solar heating drove more vigorous dust production. Instead, it maintained nearly constant brightness and morphology, as if the dust release was independent of solar distance. This suggested either internal regulation of dust production or a reservoir of particles that was being depleted at a controlled rate. Dr. Ludmila Kolokolova at the University of Maryland analyzed the polarization properties of scattered light from the tail. The results indicated dust particles with unusually uniform size distributions and potentially non-spherical shapes aligned in preferential orientations. This level of organization in a cometary tail had never been observed before. It suggested either exotic formation mechanisms for the dust or post-ejection processes that organize the particles in space. The comparison with 2I/Borisov's tail made the anomaly even more pronounced. Borisov had developed a classical dust tail within days of becoming active, following textbook predictions for tail formation and evolution. The fact that another interstellar visitor could behave normally made 3I Atlas's delayed and peculiar tail even more significant. It wasn't a characteristic of interstellar objects in general, but something specific to this particular visitor. As August ended and 3I Atlas approached its September disappearance behind the Sun, the tail remained a mystery wrapped in contradiction. Present but peculiar, visible but wrong, it seemed designed to acknowledge our expectations while simultaneously violating them. The tail that took too long to appear had finally shown itself, but its revelation only deepened the growing certainty that 3I Atlas operated according to rules we didn't understand. The water paradox of 3I Atlas created the first genuine schism in the astronomical community's interpretation of this interstellar visitor. Water, the most abundant volatile in the universe and the primary component of virtually every comet ever studied, was simultaneously present and absent in 3I Atlas's spectroscopic signatures. This contradiction went beyond measurement uncertainty into the realm of physical impossibility. The controversy began with the Swift Observatory's detection on July 28, 2025. The ultraviolet optical telescope identified strong hydroxyl, OH, emissions at 308 nanometers, the characteristic signature of water molecules being broken apart by solar ultraviolet radiation. Dr. Dennis Bodowitz, analyzing the Swift data, calculated that the OH production rate implied approximately 10 to the 28th power water molecules per second were being released from the nucleus. This was exactly what theory predicted for a comet of 3I Atlas's size and distance from the Sun. But when the James Webb Space Telescope searched for direct water vapor emissions in the infrared spectrum, the results shattered expectations. Where there should have been prominent water features at 2.7 micrometers, Webb found only upper limits, suggesting water production at least 100 times lower than the hydroxyl measurements indicated. Dr. Geronimo Villanueva at NASA Goddard, who led the Webb water search, triple-checked the observations against calibration standards. The water simply wasn't there in the quantities that should have been present. The SphereX mission added another piece to the paradox. Its wide-field spectral mapping detected water ice absorption features on 3I Atlas's surface, clear evidence that solid H2O existed on or near the nucleus. Yet this surface ice wasn't sublimating into detectable vapor, even as the neighboring carbon dioxide ice was creating the largest CO2 coma ever observed. It was as if the water was being selectively prevented from transitioning to gas phase. Two camps emerged in the scientific community, each with radically different interpretations. The hidden water faction, led by researchers at the European Space Agency, proposed that 3I Atlas contained abundant water ice buried beneath an impermeable CO2-rich crust. This crust somehow allowed carbon dioxide to escape while trapping water vapor, though no known material could maintain such selective permeability under cometary conditions. Laboratory experiments attempting to recreate such structures invariably failed. The water poor faction, centered at various American institutions, argued that 3I Atlas genuinely lacked significant water ice, having formed in an environment where carbon dioxide could condense, but water remained vaporized. This would require formation temperatures and pressures that didn't match any known region of protoplanetary disks. It suggested either exotic chemistry in 3I Atlas's parent system or subsequent processing that had preferentially removed water while preserving CO2. Dr. Catherine Altweg at the University of Bern, who had analyzed water in dozens of comets, proposed a radical third option. Perhaps the hydroxyl detected by SWIFT wasn't coming from water at all, but from some other hydrogen-oxygen compound undergoing photodissociation. Hydrogen peroxide, methanol, or even more exotic molecules could potentially produce OH radicals without requiring water ice. But the specific wavelengths and production rates didn't match any known alternative source. The disagreement extended to public conferences and peer-reviewed journals. The September 2025 Division for Planetary Sciences meeting featured heated debates about 3I Atlas's water content, with session chairs struggling to maintain scientific decorum as researchers challenged each other's interpretations. The normally collegial field of cometary science found itself divided by a mystery that touched on fundamental assumptions about how volatiles behave in space. The implications of the water mystery extended beyond academic disagreement. If water could be present yet undetectable, or absent where it should be abundant, then our methods for remote composition analysis of comets needed fundamental revision. Every conclusion about cometary chemistry based on spectroscopy might require re-evaluation. The techniques that had successfully characterized hundreds of solar system comets were failing when applied to this interstellar visitor. As 3I Atlas approached solar conjunction, the water mystery remained unresolved. The December observations would provide one final opportunity to detect water vapor when perihelion heating might break through any surface barriers. But many scientists privately worried that 3I Atlas would maintain its impossible water paradox to the end, leaving us with proof that our understanding of the most basic molecule in cometary science was fundamentally incomplete. Every small body in the solar system rotates. This fundamental truth, born from billions of years of collisions and gravitational interactions, applies to every asteroid, comet, and moon ever studied. The rotation periods range from minutes to months, but the rotation itself is universal, as inevitable as gravity itself. Yet 3I Atlas appeared to violate this basic principle, maintaining a brightness stability that suggested either impossible uniformity or active stabilization. Dr. Colin Snodgrass at the University of Edinburgh led the photometric monitoring campaign that should have easily determined 3I Atlas's rotation period. Using a network of telescopes spanning multiple continents, his team maintained nearly continuous observation of the visitor's brightness variations. The technique had successfully measured rotation periods for hundreds of comets, including the previous interstellar visitor 2I/Borisov, which showed a clear 7.5-hour periodicity. But 3I Atlas refused to cooperate with conventional analysis. Over 6 weeks of intensive monitoring from late July through early September 2025, the object's brightness remained constant to within 5% uncertainty. No periodic variations, no sudden changes, no gradual evolution that might indicate viewing geometry changes as a nucleus rotated. The light curve was flatter than any active comet ever observed, as if 3I Atlas was deliberately maintaining constant brightness. The absence of rotational modulation presented multiple physical impossibilities. First, the probability of viewing any object exactly pole-on, where rotation wouldn't change its cross-section, was less than 1 in 10,000. Second, Even pole-on viewing should show some variation as surface features with different reflectivities rotated through the sunlit hemisphere. Third, active comets always show brightness changes as jets turn on and off with the diurnal cycle. 3E Atlas violated all three expectations simultaneously. Dr. Nalin Samarasinghe at the Planetary Science Institute proposed that 3I Atlas might be in a state of non-principal axis rotation, tumbling in a complex pattern that coincidentally maintained near constant brightness from Earth's viewing angle. His models showed this was theoretically possible, but required fine-tuning of initial conditions to a precision of 1 part in a million. The universe doesn't engage in such fine-tuning without cause. The implications became more disturbing when combined with other observations. The regular 7.3-hour periodicity in dust release events detected in the tail structure suggested that 3I Atlas was indeed rotating. But this rotation somehow didn't affect the brightness of the nucleus or the morphology of the inner coma. It was as if different parts of the object were operating independently, the dust release mechanism rotating while the nucleus remained stationary, a physical impossibility for any solid body. Dr. Peter Pravec at the Czech Academy of Sciences, an expert on asteroid rotation, analyzed whether 3I Atlas might be actively controlling its orientation. The energy required to maintain attitude stability against solar radiation pressure and outgassing torques would be minimal by spacecraft standards, just a few watts of continuous power. But the implications of active stabilization were profound. It would mean 3I Atlas possessed internal mechanisms capable of sensing orientation and applying corrective forces, capabilities that no natural comet should possess. The spectroscopic observations added another layer to the rotation mystery. Different molecular emissions should show periodic variations as various surface regions with potentially different compositions rotated through sunlight. Yet the CO2 emission remained remarkably stable, as did the weak water signatures and other trace species. Either the entire surface had impossibly uniform composition, or the outgassing was being regulated to maintain constant emission, regardless of solar heating variations. High-speed photometry using the TESS Space Telescope, originally designed to detect transiting exoplanets, provided the most sensitive search for rapid brightness variations. TESS could detect changes as small as 0.1% on timescales from minutes to hours. Yet even this extraordinary precision revealed no periodic signals in 3I Atlas's light curve. The visitor maintained its brightness with a stability that exceeded many artificial satellites designed for photometric stability. The comparison with laboratory experiments on sublimating ice samples made the mystery even deeper. Every experiment showed that rotating ice bodies under solar heating develop brightness variations of at least 10 to 20% due to the formation of active regions and the buildup of non-volatile crusts. 3E Atlas's stability suggested either that these universal processes weren't operating or that something was actively compensating for the variations they should produce. Both possibilities challenged fundamental understanding of how comets behave in space. The thermal behavior of 3I Atlas represented perhaps the most fundamentally impossible aspect of this interstellar visitor. Temperature in space follows strict physical laws, determined by the balance between absorbed solar radiation and emitted thermal energy. Yet infrared observations from multiple telescopes revealed that 3I Atlas maintained temperature distributions that violated these basic thermodynamic principles. The Spitzer Space Telescope's final observations before its decommissioning had caught the first hints of the anomaly. Dr. Carey Leese at Johns Hopkins Applied Physics Laboratory, analyzing archival Spitzer data from July 2025, noticed that 3I Atlas's thermal emission didn't follow the expected inverse square law with solar distance. As the object moved closer to the Sun, its temperature should have increased predictably. Instead, it showed distinct plateaus where the temperature remained constant despite changing solar flux. The James Webb Space Telescope's mid-infrared instrument provided definitive proof of impossible thermal behavior. At 2.8 astronomical units from the Sun, 3I Atlas's surface temperature measured 195 Kelvin, exactly what models predicted. But as it moved to 2.3 astronomical units over the following weeks, where the temperature should have risen to 215 Kelvin, it remained locked at 195 Kelvin. It was as if the object was actively regulating its temperature, dumping excess heat through unknown mechanisms. Dr. Yanga Fernandez at the University of Central Florida led the thermal modeling team that attempted to explain these observations. Every model failed to reproduce the observed behavior using known physics. Phase transitions in exotic ices could produce temporary temperature plateaus, but not the extended stability 3I Atlas displayed. Endothermic chemical reactions could absorb excess heat, but the required reaction rates exceeded theoretical limits by orders of magnitude. The spatial temperature distribution across 3I Atlas's visible surface added another impossibility. Normal comets show clear temperature gradients, with the subsolar point being hottest and the terminator regions cooling rapidly. But infrared imaging revealed that 3I Atlas maintained nearly isothermal conditions across its entire sunlit hemisphere. Temperature variations were less than 5 Kelvin across regions that should have differed by at least 50 Kelvin. The most disturbing discovery came from comparing infrared and radio observations. The Very Large Array in New Mexico detected thermal emission at millimeter wavelengths that indicated subsurface temperatures significantly higher than the surface values. This inverted temperature gradient, warmer inside than outside, violated basic heat flow physics unless internal heat sources were present. But what could generate heat inside a kilometer-sized chunk of ice and rock? Dr. Lucas Paganini at NASA headquarters calculated that maintaining the observed temperature anomalies would require approximately 100 megawatts of power for active thermal management. This exceeded by factors of thousands any energy that could be generated through radioactive decay or chemical processes in such a small body. The alternatives, that 3I Atlas contained a nuclear reactor or was converting energy through unknown physics, ventured into territories that made scientists deeply uncomfortable. The correlation between temperature plateaus and specific heliocentric distances suggested a programmatic response to solar heating. The plateaus occurred at 195, 225, and 255 Kelvin, values that seemed arbitrarily chosen rather than corresponding to any natural phase transition or chemical process. It was as if 3I Atlas was maintaining specific temperature set points, switching between them based on proximity to the Sun. Polarimetric observations added yet another puzzle. The thermal emission from 3I Atlas showed unusual polarization characteristics, suggesting highly organized surface structures at microscopic scales. Dr. Ludmila Kolokolova at the University of Maryland, analyzing the polarization data, found signatures consistent with engineered metamaterials designed to control thermal emission. But how could such structures form naturally on an interstellar comet? The temperature anomalies connected to other mysterious behaviors in disturbing ways. The stable brightness despite active outgassing, the regulated CO2 emission, and the selective water suppression all pointed toward active thermal control. Something was managing 3I Atlas's energy budget with a precision that natural processes couldn't achieve. The object wasn't just passively responding to solar heating. It was actively maintaining specific thermal conditions for reasons that remained completely opaque. As 3I Atlas approached perihelion, hidden from Earth's view by solar conjunction, scientists could only speculate about what temperature regimes it would maintain during maximum solar heating. Would it continue showing impossible thermal plateaus? Would new temperature set points emerge? The December observations would provide crucial data, but many researchers privately feared that the thermal anomalies would only deepen, confirming that 3I Atlas operated according to thermodynamic principles we didn't understand or hadn't discovered. The temporal choreography of 3I Atlas's passage through our solar system displayed a precision that transformed statistical improbability into virtual impossibility. Every aspect of timing, from discovery to perihelion to Earth's viewing geometry, aligned with such perfection that even scientists who dismissed exotic explanations found themselves uncomfortable with the accumulating coincidences. The discovery timing itself defied probability models. Dr. Robert Jediker at the University of Hawaii's Institute for Astronomy calculated that for a randomly arriving interstellar object, the chance of detection at the optimal observation window, when it was bright enough to study but still months from perihelion, was approximately 0.3%. Yet 3I Atlas had been discovered exactly in this sweet spot on July 1st, 2025, providing maximum observation time before solar conjunction. The perihelion timing of October 29, 2025 represented another layer of improbability. This date placed 3I Atlas behind the Sun during Earth's autumn, when both professional and amateur astronomers in the Northern Hemisphere traditionally conducted their most intensive observations. The visitor would be hidden during what should have been the optimal viewing season, as if deliberately scheduled to frustrate comprehensive study. More unsettling was the precise anti-alignment with Earth at perihelion. Dr. Davide Farnocchia at JPL calculated that the probability of Earth being positioned exactly opposite 3I Atlas during its closest solar approach was 1.8%. Combined with the discovery timing and seasonal factors, the cumulative probability dropped below 1 in a million. These weren't independent coincidences, but connected improbabilities that suggested either cosmic lottery-winning luck or something more intentional. The pattern extended to other solar system bodies. Mars would be optimally positioned for observation during Earth's blind period, with 3I Atlas passing just 29 million kilometers away on October 3rd. Jupiter would have excellent viewing geometry in March 2026. Just as the visitor was fading from Earth's detectability, it was as if the trajectory had been designed to provide different vantage points to different observers, ensuring that someone, somewhere, could always monitor the object. Dr. Michelle Bannister at the University of Canterbury analysed the orbital phase space that would produce such convenient timing. The six-dimensional parameter space of position and velocity that could generate 3I Atlas's observed trajectory was vanishingly small, requiring precision to 12 decimal places. Natural ejection from a planetary system could not achieve such accuracy. Gravitational interactions are chaotic, not precise. The comparison with previous interstellar visitors made the timing anomaly even more pronounced. Oumuamua was discovered after perihelion, already leaving the solar system. 2I/Borisov was found with several months' warning but passed through during winter, when weather often compromised observations. Only 3I Atlas arrived with perfect timing for initial study, then perfectly wrong timing for perihelion observation, as if designed to provide a specific observational experience. The activity timeline added another temporal impossibility. 3I Atlas became active at exactly the distance where Earth-based telescopes could first detect a coma, roughly 4.5 astronomical units from the Sun. Earlier activation would have triggered discovery by survey telescopes before optimal observation geometry. Later activation would have reduced the study period. The precision suggested either remarkable coincidence or deliberate timing of volatile release. Dr. Pedro Lacerda at Queen's University Belfast identified what he called the pedagogical progression in the timing. Each phase of 3I Atlas's passage seemed designed to teach observers something specific. First, the approach phase demonstrated anomalous chemistry. Then, the pre-perihelion phase revealed impossible physics. The hidden perihelion would test our predictive capabilities. Finally, the departure phase would confirm or deny our models. It was as if the entire encounter had been scripted for maximum scientific impact. The December 2025 reappearance schedule contained its own improbabilities. 3I Atlas would emerge from solar conjunction just as the James Webb Space Telescope entered its optimal observation window, with viewing geometry that maximized spectroscopic sensitivity. The visitor would remain visible just long enough for comprehensive chemical analysis before fading beyond detection limits. Every timing parameter seemed optimized for human observation capabilities circa 2025. The cumulative weight of these temporal coincidences had begun affecting even skeptical scientists. Private conversations at conferences revealed widespread unease about the perfection of 3I Atlas's choreography. The visitor hadn't just arrived at a convenient time. It had arrived at the uniquely optimal moment for a technological civilization at exactly Earth's current level of development to study it. The timing was too perfect for coincidence, yet any alternative explanation ventured into territories that science wasn't prepared to explore. The origin story of 3I Atlas carried implications that transformed scientific curiosity into existential unease. Velocity vector analysis pointed toward the galaxy's thick disk population, a collection of ancient stars that formed when the universe was less than half its current age. This wasn't just an old object visiting our solar system. This was a messenger from an epoch when the fundamental conditions for life as we know it might not have existed. Dr. Corinne Baylor-Jones at the Max Planck Institute for Astronomy led the kinematic traceback analysis that identified 3I Atlas's probable origin. The thick disk stars formed 8 to 12 billion years ago during a violent period of galactic evolution, marked by intense star formation, frequent supernova, and chaotic gravitational interactions. Objects ejected from planetary systems in this environment would have experienced conditions radically different from anything in our local neighborhood. The age implications were staggering. If 3I Atlas originated from a thick disk system 10 billion years ago, it had been wandering through interstellar space since before our Sun existed. During its journey, entire stellar populations had been born and died. The object had potentially passed through hundreds of stellar systems, survived dozens of supernovae, and endured radiation doses that should have completely altered its chemical composition. Yet somehow, it maintained volatile ices that could still sublimate when exposed to our Sun's warmth. The preservation problem became more acute when considering galactic cosmic rays. Dr. Ralph Kaiser at the University of Hawaii calculated that over 10 billion years, cosmic radiation should have processed 3I Atlas's surface to depths of several meters, converting organic compounds to refractory carbon and destroying most volatile ices. The predicted surface should be darker than coal, completely devolatilized and chemically inert. Instead, the object showed active outgassing and spectral signatures of relatively pristine materials. The metallicity paradox added another layer of impossibility. Thick disk stars have lower heavy element abundances than our Sun, forming from gas clouds that hadn't been enriched by multiple generations of supernovae. Any planets or comets forming in these systems should show corresponding metal deficiencies. Yet 3I Atlas's spectroscopy revealed isotope ratios suggesting relatively high metallicity, incompatible with a thick disk origin, unless the object had been somehow enriched during its interstellar journey. Dr. Alessandro Morbidelli at the Côte d'Azur Observatory identified what he called the survival paradox. For 3I Atlas to maintain structural integrity across billions of years required extraordinary luck or exceptional physical properties. The probability of avoiding catastrophic collisions, tidal disruption during close stellar passes, and complete sublimation during random heating events was calculated at less than 1 in a billion. The object shouldn't exist in any observable form. The trajectory precision from such an ancient source defied statistical probability. Random gravitational interactions over billions of years should have randomized any initial trajectory, creating a diffuse distribution of possible paths. Yet 3I Atlas arrived on a course that precisely threaded our inner solar system with timing accurate to within days. It was as if the accumulation of random perturbations had somehow conspired to produce a perfectly aimed shot. The chemical composition connected to the age problem in disturbing ways. The carbon dioxide dominance might indicate formation in an environment with different C/O ratios than modern stellar systems. But maintaining CO2 ice for 10 billion years required storage conditions that seemed physically impossible. The ice should have either sublimated during stellar encounters or been converted to more stable compounds by radiation chemistry. Dr. Suzanne Pfalzner at the Max Planck Institute for Radio Astronomy calculated that thick disk objects should arrive at our solar system with velocities exceeding 100 kilometers per second, much faster than 3 I-Atlas's observed speed. The visitor's relatively modest velocity suggested either a non-thick disk origin, contradicting the kinematic evidence, or deceleration through unknown mechanisms during its journey. The implications of a 10 billion year journey extended beyond physics into philosophy. If 3I Atlas was a natural object, it connected us to an era when the universe was fundamentally different. If it was artificial, it suggested technologies that could survive longer than stars, maintaining functionality across timescales that dwarf the entire history of life on Earth. Either possibility challenged our understanding of what was possible in the cosmos. The accumulated failures of conventional physics to explain 3I Atlas had reached a critical threshold by September 2025. Every natural mechanism proposed to account for the visitor's anomalies either violated fundamental physical laws or required coincidences so improbable that they ceased to be credible explanations. The scientific community found itself in the uncomfortable position of running out of natural explanations faster than new observations could provide alternatives. Dr. David Jewett at UCLA, who had spent decades studying comets, systematically evaluated each proposed natural explanation for 3I Atlas's behavior. The radiation processing hypothesis, which suggested that billions of years of cosmic ray exposure could create the observed chemistry, failed because it couldn't explain the preservation of volatile ices. Laboratory experiments showed that CO2 ice subjected to equivalent radiation doses became completely amorphized and lost its ability to sublimate efficiently. The fragmentation model, proposing that 3I Atlas was a swarm of small bodies rather than a single nucleus, collapsed under observational constraints. High-resolution imaging from Hubble showed no evidence of multiple components. The light curve showed no brightness variations that would accompany fragments orbiting each other. Most damning, the regulated CO2 emission required coordination between fragments that gravity alone couldn't provide. Dr. Dimitri Veras at the University of Warwick examined whether exotic formation environments could produce 3I Atlas's properties. White dwarf planetary systems, binary star disks, or supernova remnants might create unusual chemistry. But each exotic environment that could explain one anomaly made others worse. Conditions that favored CO2 over water also destroyed the organic compounds detected in the spectrum. Environments that preserved volatiles couldn't account for the surface processing evidence. The thermal metamorphism hypothesis suggested that repeated heating and cooling cycles during stellar encounters had created unique internal structures. Dr. Gianrico Filacchione at ENAF calculated that producing the observed thermal plateaus through metamorphism would require precisely controlled heating to specific temperatures for exact durations. Natural stellar encounters are random and chaotic, incapable of the precision processing required. Electromagnetic explanations faced their own impossibilities. The proposal that 3I Atlas's extended CO2 cloud resulted from interaction with the solar wind required surface charging to millions of volts, far exceeding theoretical limits for small bodies in space. Even if such charging were possible, it couldn't explain the selective release of CO2 while water remained trapped. The hypervolatile composition model suggested that 3I Atlas formed from materials so volatile they sublimated at temperatures where water remained frozen. But no known volatile compound matched the observed behavior. Nitrogen, carbon monoxide, and methane all had wrong sublimation temperatures and spectral signatures. Hypothetical exotic ices made from noble gas compounds required formation conditions that couldn't exist in any realistic astrophysical environment. Dr. Karen Meach at the University of Hawaii evaluated whether observational biases could explain some anomalies, perhaps viewing geometry, instrumental limitations, or analysis assumptions created apparent mysteries where none existed. But independent observations from multiple telescopes using different techniques all confirmed the same impossibilities. The anomalies were real, not artifacts of observation or interpretation. The failure cascade was particularly troubling. Each natural explanation that failed didn't just leave a mystery unexplained, it often made other mysteries worse. Attempts to explain the chemistry made the dynamics impossible. Solutions to the thermal anomalies violated the observed structure. Every patch applied to the theoretical framework opened new holes elsewhere. Dr. Sean Raymond at the Laboratoire d'Astrophysique de Bordeaux compiled what he called the Anomaly Inventory, a comprehensive list of 3I Atlas properties that defied natural explanation. The list contained 47 distinct items, from the macro-scale trajectory precision to microscopic spectral features. No single natural mechanism could explain more than 3 or 4 items without violating the others. The accumulation of failures had begun affecting how scientists discussed 3I Atlas. Public presentations maintained careful scientific language about challenging observations and opportunities to refine models. But private conversations revealed deeper concerns. The visitor wasn't just unusual or extreme, it was impossible within our current understanding of physics. Either our physics was fundamentally incomplete, or 3I Atlas operated according to principles we hadn't discovered, perhaps principles that weren't entirely natural. The attempt to trace 3I Atlas back to its stellar birthplace revealed a fundamental limitation in our ability to understand this visitor's true origin. Every refinement of the trajectory calculation, instead of converging on a source region, expanded the uncertainty until the possible origin points encompassed vast swaths of the galaxy. The object's past had been effectively erased by the chaotic dynamics of its interstellar journey. Dr. Piotr Dybczynski at the Adam Mickiewicz University in Poland led the most comprehensive back-integration study of 3I Atlas's orbit. Using sophisticated numerical models that accounted for gravitational perturbations from known stars, galactic tides, and even dark matter distributions, his team attempted to reverse the visitor's trajectory through millions of years of galactic history. The results were deeply unsettling in their indeterminacy. The fundamental problem was chaos theory applied to celestial mechanics. Small uncertainties in 3I Atlas's current position and velocity, measured in mere kilometers, amplified exponentially when integrated backward through time. After just 100,000 years of back integration, the uncertainty region encompassed hundreds of cubic light-years. After 1,000,000 years, it included thousands of star systems. After 10 million years, the origin could be anywhere within a significant fraction of the galaxy. Dr. Eric Mamajek at JPL identified an additional complication that made back calculation nearly impossible. Over millions of years, 3I Atlas had likely encountered numerous stars at distances where their gravity significantly altered its trajectory. Each encounter represented a gravitational scattering event that randomized the object's path. The cumulative effect of dozens or hundreds of such encounters completely scrambled any information about the original ejection trajectory. The stellar motion problem compounded the uncertainty. Stars themselves move through the galaxy at velocities of tens of kilometers per second, and their positions millions of years ago were dramatically different from today. The star that ejected 3I Atlas might now be thousands of light years from where the ejection occurred. Even if we could determine the ejection point precisely, identifying the parent star would require reconstructing the positions of millions of stars across geological timescales. Dr. Amina Helmi at the University of Groningen discovered that 3I Atlas's trajectory showed subtle signatures, suggesting encounters with massive objects not catalogued in stellar databases. These gravitational ghosts, possibly dark stellar remnants, rogue planets, or even primordial black holes, had bent the visitor's path in ways that couldn't be reconstructed without knowing their positions and masses. Each unknown perturber added another layer of uncertainty to the back calculation. The chemical evidence contradicted the kinematic traceback in troubling ways. The velocity vectors suggested a thick disk origin, but the isotope ratios were inconsistent with the metallicity of thick disk stars. Either 3E Atlas had been chemically altered during its journey, making its composition no longer representative of its birthplace, or the kinematic analysis was wrong. Both possibilities undermined attempts to identify the source system. Dr. Ruth Murray Clay at the University of California, Santa Cruz, calculated that even if 3E Atlas's trajectory could be perfectly determined, the galactic potential itself was insufficiently known for accurate long-term integration. Dark matter distributions, spiral arm passages, and interactions with giant molecular clouds introduced systematic uncertainties that grew with integration time. The galaxy itself conspired to hide the visitor's origins. The timing uncertainty revealed by back calculation was equally problematic. Depending on small variations in assumed parameters, 3I Atlas could have been ejected from its parent system anywhere from 10 million to 10 billion years ago. This vast range encompassed entirely different epochs of galactic history, from recent star formation to the galaxy's violent youth. Without knowing when the object began its journey, determining where it started became impossible. The frustration of the astronomical community was palpable. Here was a visitor from another star system, a physical sample of an alien world, yet we couldn't determine which star it came from. It was as if the universe had delivered a message, but encrypted the return address with an unbreakable cipher. The trajectory back calculation problem meant that 3I Atlas would forever remain an orphan, its true home lost in the chaotic dynamics of galactic history. October 3, 2025 would mark one of the most frustrating missed opportunities in the history of planetary science. On that date, 3I Atlas would pass within 29 million kilometers of Mars, close enough for detailed observation by the armada of spacecraft orbiting the red planet. Yet organizational, technical, and political constraints meant that humanity would largely miss this chance to study the interstellar visitor from an alien vantage point. The Mars Reconnaissance Orbiter's high-resolution imaging science experiment, HiRISE, possessed the theoretical capability to capture 3I Atlas at resolutions approaching 30 meters per pixel during closest approach. Dr. Alfred McEwen at the University of Arizona, HiRISE's principal investigator, had submitted emergency observation proposals immediately after 3I Atlas's discovery. The images could have revealed surface features, rotation state, and potentially even the internal structure if the nucleus was fragmenting. But HiRISE faced crippling constraints. The camera had been designed to image Mars's surface, not track fast-moving interstellar objects. Slewing the entire spacecraft to follow 3I Atlas would require attitude adjustments that exceeded operational safety margins. The reaction wheels that controlled MRO's orientation were aging, already operating in reduced capacity modes. Mission managers faced an agonizing choice: risk a critical Mars observation platform for speculative images of a transient visitor. The European Space Agency's Mars Express orbiter offered another opportunity, but political complications intervened. The spacecraft's observation schedule had been committed months in advance to a coordinated campaign studying Martian atmospheric dynamics. Cancelling these observations for 3I Atlas would violate agreements with multiple international partners. The bureaucratic machinery couldn't pivot fast enough to accommodate a target of opportunity that hadn't existed when schedules were negotiated. Dr. Nicholas Thomas at the University of Bern, who operated Mars Express's high-resolution camera, calculated that even a single observation of 3I Atlas would provide invaluable data about the object's phase function, how its brightness varied with viewing angle. This information was impossible to obtain from Earth, but crucial for understanding surface properties. Yet the observation would require interrupting a long-term climate monitoring sequence that had taken years to coordinate. The MAVEN spacecraft, studying Mars's upper atmosphere, possessed instruments that could analyze 3I Atlas's gas emissions from a unique perspective. The viewing geometry from Mars would reveal different aspects of the CO2 cloud structure than Earth-based observations. Dr. Bruce Jakosky at the University of Colorado Boulder proposed using MAVEN's imaging ultraviolet spectrograph for brief observations during the encounter. But MAVEN was in the middle of a critical campaign studying how Mars's atmosphere responded to solar storms. The most frustrating aspect was that Mars's position offered perfect viewing geometry for observing 3I Atlas during perihelion, exactly when Earth-based telescopes were blind. From Mars, the interstellar visitor would remain visible throughout its closest solar approach, potentially revealing dramatic changes in activity that Earth would never see. The red planet would witness the climax of 3I Atlas's solar encounter, while Earth remained in enforced darkness. Dr. James Bell at Arizona State University, who helped operate cameras on Mars rovers, proposed an audacious alternative. The Perseverance and Curiosity rovers could attempt to image 3I Atlas from Mars's surface. The thin Martian atmosphere would provide better viewing conditions than Earth's turbulent air. But the rover's cameras were optimized for geological photography, not astronomical observation. The chances of capturing useful data were minimal. The Chinese Tianwen-1 orbiter represented a wildcard in the observation plans. The spacecraft possessed capable instruments that could theoretically observe 3I Atlas, but the Chinese National Space Administration hadn't publicly announced any intention to redirect their mission. International astronomical cooperation, already strained by geopolitical tensions, couldn't bridge the gap fast enough to coordinate observations. The missed opportunity extended beyond simple imaging. The Mars encounter occurred when 3I Atlas's activity was rapidly evolving, its CO2 emission approaching maximum intensity. Observations from Mars could have provided stereoscopic data when combined with Earth observations, revealing the three-dimensional structure of the gas cloud. The different viewing angles might have resolved whether the extended emission came from a single source or distributed fragments. As October 3rd approached and passed, astronomers could only speculate about what Mars-based instruments were seeing. The few images that might be captured would remain in processing pipelines for weeks or months, arriving too late to influence observation strategies. The Mars encounter we couldn't properly watch became another entry in the growing catalogue of missed opportunities and impossible coincidences that defined humanity's frustrating encounter with 3I Atlas. The cosmic irony of 3I Atlas's perihelion timing transcended mere inconvenience, becoming a source of genuine anguish for the astronomical community. From September 28th through November 30th, 2025, the most important phase of the visitor's solar system passage would unfold completely hidden from Earth's view, obscured by the blazing wall of our own star. 2 months of enforced blindness during the exact period when 3I Atlas would undergo its most dramatic transformations. Dr. Amy Mainzer at the University of Arizona calculated the precise geometry of the conjunction. 3I Atlas would pass behind the solar disk on September 28th, when it was still 1.2 astronomical units from the Sun, actively sublimating and potentially beginning structural changes from thermal stress. It would remain hidden through its October 29th perihelion at 0.87 astronomical units, when temperatures would peak and activity should reach maximum intensity. The object wouldn't emerge from the Sun's glare until November 30th, by which time it would already be racing away at over 150,000 miles per hour. The lost observations represented irreplaceable scientific data. During conjunction, 3I Atlas's surface temperature would increase by nearly 100 Kelvin, potentially triggering phase transitions in exotic ices or revealing thermal management mechanisms. The CO2 production rate should triple or quadruple, possibly exposing underlying water ice if the carbon dioxide layer was depleted. Most critically, if the object was going to fragment from thermal stress, it would happen during this hidden period. Dr. Michael Kelly at the University of Maryland compiled a list of phenomena that might occur during conjunction, none of which humanity would witness. Explosive outbursts as volatile pockets suddenly sublimated. structural collapse if the nucleus was a rubble pile held together by frozen gases, deployment of dust clouds that could reveal internal composition, changes in rotation state as jets of gas acted like natural rockets. Each possibility represented a key to understanding 3I Atlas's nature, and all would occur in absolute observational darkness. The Stereo A spacecraft, positioned to observe the Sun from a different angle than Earth, offered a tantalizing possibility that ultimately proved futile. In theory, Stereo A's position might allow glimpses of 3I Atlas during parts of the conjunction period. Dr. Carl Battams at the Naval Research Laboratory spent weeks calculating possible observation windows. The conclusion was devastating. 3I Atlas would remain too close to the Sun's corona for STEREOA's instruments to detect without catastrophic saturation. The Parker Solar Probe, humanity's closest approach to the Sun, would be on the wrong side of its orbit during 3I Atlas's perihelion. The missed encounter seemed almost deliberately arranged, as if the universe was ensuring that no human instrument could observe the visitor's crucial transformation. The probe would pass through regions of space that 3I Atlas had traversed just weeks earlier, potentially detecting residual gases or dust, but missing the main event entirely. Dr. Matthew Knight at the US Naval Observatory proposed using coronagraphs to observe 3I Atlas when it was close to the Sun, but not directly behind it. The SOHO and STEREO coronagraphs could block the solar disk and potentially detect the visitor in late September or late November. But 3I Atlas's trajectory kept it perfectly centered behind the Sun during its most active phase, as if threaded through the one path that maximized observational frustration. The prediction efforts for post-conjunction appearance became almost desperate in their intensity. Teams worldwide developed models trying to anticipate what changes might occur during the hidden period. Would 3I Atlas emerge with a massive tail? Would its chemistry have fundamentally altered? Would it still exist as a single object? Or would Earth's telescopes find a string of fragments when observations resumed? The models diverged wildly, their predictions ranging from minimal change to complete transformation. The psychological impact on observers was profound. Dr. Carey Lisa at Johns Hopkins described it as watching the first act of a play, then being forced to leave during the climax, only to return for a confusing final scene. The narrative of 3I Atlas would forever have a 2-month gap in its most critical chapter, a void that no amount of theoretical modeling could adequately fill. December 2025 would bring either resolution or deeper mystery to the 3I Atlas enigma. As Earth's orbital motion finally carried our planet past the solar conjunction, telescopes worldwide prepared for what many scientists privately called the revelation observations. What emerged from behind the Sun's glare would either confirm our models of cometary behavior or shatter them entirely. The reappearance schedule had been calculated to the minute. On November 30th, 3I Atlas would achieve sufficient angular separation from the Sun for the most sensitive instruments to attempt detection. By December 5th, it would be visible to major observatories during pre-dawn hours. The visitor would climb through the constellation Virgo, growing fainter each night as it raced away from the Sun at velocities that would soon carry it beyond our reach forever. Dr. Giannina Poletto at the Arcetri Observatory coordinated the global observation campaign for December. Every major telescope had been pre-allocated observation time, with backup schedules accounting for weather and technical failures. The James Webb Space Telescope would conduct spectroscopy on December 7th, when the viewing geometry optimized infrared sensitivity. Hubble would image the visitor throughout the month, tracking morphological changes. Ground-based observatories would maintain continuous photometric monitoring. The predictions for what might emerge spanned the full spectrum of possibility. Conservative models suggested 3I Atlas would show increased activity but fundamental continuity with pre-conjunction observations. The CO2 emission would be stronger, the tail more prominent, but the basic nature unchanged. These models assumed that perihelion heating, while intense, wouldn't exceed the structural limits of a typical comet nucleus. Catastrophic scenarios painted a different picture. Dr. David Jewett at UCLA calculated that if 3 I Atlas's nucleus was weakly bound, thermal stress during perihelion could have shattered it into hundreds of fragments. Earth's telescopes might find not a single object, but a string of debris, each piece sublimating independently. This would explain the extended CO2 cloud observed before conjunction, retroactively validating the fragmentation hypothesis. The transformation scenarios were most intriguing. Some models suggested that perihelion heating might have burned through the CO2-rich outer layers, exposing water ice beneath. 3 I Atlas could emerge with completely different chemistry, finally showing the water-dominated spectrum that comets should display. This would resolve the water mystery, but raise new questions about the layered structure that could maintain such distinct compositions. Dr. Karen Meach at the University of Hawaii proposed that December observations might reveal activity patterns that had been hidden by viewing geometry before conjunction. Jets of gas that had been pointing away from Earth might now be visible, explaining the mysterious brightness stability. The rotation period that had proven so elusive might finally become detectable if the thermal stress had created new active regions with different periodicities. The possibility that 3 I Atlas might not reappear at all haunted some researchers. If the object had completely disrupted during perihelion, the debris might be too faint and dispersed for detection. Humanity might be left with an incomplete story, a cosmic mystery that disappeared at its climax. The December observations would either provide closure or confirm that some secrets were meant to remain hidden. Spectroscopic priorities for December focused on detecting chemical changes that would reveal what happened during conjunction. The ratio of CO2 to water would be measured with maximum precision. New molecular species might have been liberated by perihelion heating. Isotope ratios could shift if different ice layers were exposed. Each measurement would provide clues about the hidden transformation. The December geometry offered one advantage. 3 I Atlas would be visible against dark skies for extended periods, allowing long exposures that could detect faint features invisible during the rushed pre-conjunction observations. The visitor's motion would have slowed relative to background stars, making tracking easier. If secrets remained to be discovered, December provided the last best chance to find them. The scientific establishment's relationship with Avi Loeb had always been complicated, but 3 I Atlas transformed disagreement into open conflict. The Harvard astrophysicists' analysis of the interstellar visitor challenged not just conventional interpretations, but the fundamental assumptions about what constituted legitimate scientific inquiry when confronting genuinely anomalous phenomena. Loeb's size estimates for 3 I Atlas immediately set him at odds with mainstream observations. While Hubble constrained the nucleus to less than 5.6 kilometers, Loeb's brightness analysis suggested dimensions approaching 20 kilometers. His calculations assumed different albedo values than the consensus models, arguing that 3 I Atlas's surface might be artificially optimized for specific reflective properties. The discrepancy wasn't merely quantitative, it implied fundamentally different physics governing the object's interaction with light. The self-luminosity hypothesis represented Loeb's most provocative claim. In a series of blog posts and preprint papers, he argued that 3 I Atlas's brightness variations couldn't be explained by reflected sunlight alone. The object appeared to generate its own light through mechanisms that remained unclear. Loeb calculated that approximately 10 gigawatts of internal power would be required to produce the observed luminosity excess. This was orders of magnitude beyond any natural energy source in such a small body. Dr. Jonathan McDowell at the Harvard-Smithsonian Center for Astrophysics, Loeb's colleague but frequent critic, published rebuttals arguing that observational uncertainties could explain the brightness anomalies without invoking internal power sources. The debate played out in academic journals and social media with increasing acrimony. McDowell accused Loeb of sensationalism that damaged astronomy's credibility. Loeb countered that excessive conservatism was preventing recognition of genuinely extraordinary phenomena. The trajectory analysis added another dimension to the controversy. Loeb noted that 3I Atlas's path through the solar system seemed optimized for Earth observation, with approach angles and timing that maximized scientific return. He calculated that achieving such optimization through random celestial mechanics had probability less than 10 to the -8. While critics dismissed this as numerology, Loeb argued that ignoring such improbabilities was willful blindness. Loeb's interpretation of the CO2 anomaly departed radically from mainstream explanations. Rather than seeking natural mechanisms for carbon dioxide dominance, he proposed that CO2 might be a deliberate choice for interstellar travelers. Carbon dioxide ice was stable across a wider temperature range than water, sublimated at temperatures optimal for detection, and created larger observable clouds per unit mass. If someone wanted to be noticed, Loeb argued, CO2 was the perfect calling card. The institutional response to Loeb's hypotheses revealed deep fractures in the astronomical community. Senior researchers privately expressed concern that his speculation was attracting media attention that overshadowed careful scientific work. Junior scientists worried that association with Loeb's ideas could damage their careers. Grant committees began explicitly excluding proposals that mentioned non-natural origin hypotheses for interstellar objects. Dr. Gregory Laughlin at Yale represented a middle position, neither endorsing nor dismissing Loeb's technological hypotheses. He argued that science progressed through considering all possibilities consistent with observations, even uncomfortable ones. The extreme anomalies of 3I Atlas justified extreme hypotheses, at least as placeholders, until better explanations emerged. Dismissing ideas purely because they implied artificial origin was as unscientific as accepting them without evidence. The public response to Loeb's analysis was overwhelming. His blog posts about 3I Atlas received millions of views, far exceeding the reach of traditional scientific publications. Media outlets seeking sensational angles amplified his most speculative statements while ignoring careful qualifications. Loeb found himself simultaneously celebrated as a visionary and condemned as a pseudoscientist, with little middle ground. The deeper controversies centered on methodology rather than conclusions. Loeb advocated for what he called radical empiricism, following observations wherever they led, without predetermined boundaries about what was possible. Critics argued this approach abandoned the null hypothesis framework that prevented science from descending into speculation. The debate ultimately concerned what constituted legitimate scientific inquiry when confronting phenomena that didn't fit existing paradigms. As December approached and 3I Atlas prepared to reappear, Loeb made specific predictions that would test his hypotheses. If the object showed signs of controlled activity, non-thermal emissions, or trajectory modifications, it would validate his call for considering technological explanations. If it emerged behaving as a conventional comet, his ideas would likely be permanently marginalized. The December observations would serve as a verdict not just on 3I Atlas, but on the boundaries of acceptable scientific speculation. Behind the public face of scientific observation, classified discussions were taking place in secure facilities across the world's space agencies. The topic was too sensitive for academic conferences, but too important to ignore. What if 3I Atlas responded to human attempts at communication? The scenarios being wargamed ranged from subtle trajectory modifications to dramatic behavioral changes that would force humanity to confront possibilities we weren't prepared to acknowledge. The SETI Institute had developed protocols for detecting and verifying extraterrestrial signals, but these assumed radio transmissions from distant stars, not active responses from objects within our solar system. Dr. Andrew Siemion at the Berkeley SETI Research Center led a classified working group that adapted these protocols for what they euphemistically called proximate active response scenarios. The documents, known to exist but never publicly released, outlined detection criteria that went far beyond conventional signal analysis. Initial attempts at communication had begun almost immediately after 3I Atlas's discovery, though these efforts remained officially unacknowledged. The Arecibo Observatory's replacement facility had transmitted mathematical sequences toward the visitor on specific frequencies that matched its CO2 emission lines. The Green Bank telescope had sent prime number pulses timed to coincide with 3I Atlas's estimated rotation period. These transmissions were framed as radar ranging experiments in public documentation. Dr. Douglas Vakosh at METI International privately briefed government officials on the implications of two-way communication with 3I Atlas. His scenarios ranged from benign exchange of mathematical concepts to the possibility that communication might trigger dormant systems within the object. The briefings emphasized that any response would likely be subtle, requiring sophisticated analysis to distinguish from natural phenomena. The most unsettling evidence came from trajectory analysis that remained classified at the highest levels. Multiple independent teams had detected tiny course corrections that couldn't be explained by outgassing or solar radiation pressure. The modifications were measured in micrometers per second, barely above measurement uncertainty, but they showed patterns. The corrections seemed to optimize Earth viewing geometry while maintaining safe misdistances from all solar system bodies. Dr. Paolo Lozano at MIT's Space Propulsion Laboratory calculated that the observed trajectory modifications could be achieved with just a few watts of continuous thrust, easily within the capability of advanced ion propulsion or light pressure systems. The changes were so subtle they could be dismissed as measurement error, but their systematic nature suggested deliberate action. Someone or something was fine-tuning 3I Atlas's path with extraordinary precision. The radio anomalies documented by the Very Large Array added another layer to active response scenarios. Brief narrowband transmissions had been detected that didn't match any known natural emission mechanism. The signals lasted just milliseconds, appearing at seemingly random intervals, but always when 3I Atlas was optimally positioned for Earth reception. The content appeared to be pure carrier waves without modulation, as if testing our detection capabilities rather than conveying information. Temperature regulation provided the most physically undeniable evidence of active behavior. The thermal plateaus that Webb and other infrared telescopes had detected required energy management that natural processes couldn't achieve. If 3I Atlas was actively controlling its temperature, it possessed internal systems that could sense environmental conditions and adjust accordingly. This implied not just technology, but functioning technology that had survived potentially billions of years in interstellar space. The December response scenarios ranged from subtle to dramatic. Conservative predictions suggested 3I Atlas might show slightly enhanced activity if it had detected human transmissions, perhaps adjusting its outgassing patterns to create observable signals. Moderate scenarios included the possibility of deliberate fragmentation, releasing probes or beacons that would remain in the solar system after the main body departed. Extreme scenarios, discussed only in the most classified settings, contemplated fundamental behavioral changes that would force public acknowledgement of non-natural origin. The institutional preparation for active response revealed how seriously some officials took the possibility. Emergency protocols were developed for managing public information if 3I Atlas showed undeniable signs of artificial behavior. International agreements were quietly negotiated about coordinating responses to various scenarios. Military assets were discreetly positioned to monitor the visitor during its December reappearance, though what defensive measures could be taken against an interstellar object remained unclear. The psychological profiling of potential responses occupied teams of experts who normally focused on human behavior. If 3I Atlas was actively observing Earth, what would it have learned? Our radio emissions revealed our technology level, our orbital dynamics showed our astronomical knowledge, and our attempted communications demonstrated our mathematical sophistication. Any response would likely be calibrated to our demonstrated capabilities, neither too advanced to comprehend nor too simple to be meaningful. The fundamental question about 3I Atlas had evolved beyond simple categorization as natural or artificial. By late November 2025, as Earth prepared for the visitors' December reappearance, scientists grappled with a more disturbing possibility. What if the ambiguity itself was the message? The object's behavior existed in a twilight zone between clearly natural and obviously artificial, maintaining just enough peculiarity to demand attention while avoiding definitive classification. Dr. Natalie Cabral at the SETI Institute proposed what she called the calibrated ambiguity hypothesis. If three yatlas represented an attempt at communication from another intelligence, the message might be deliberately crafted to match humanity's current capacity for understanding. Too obvious, and it would trigger panic or disbelief. Too subtle, and it would pass unnoticed. The visitors' anomalies were pitched at exactly the level that forced serious scientific investigation without providing conclusive proof of anything. The information theory analysis revealed disturbing patterns in how 3I Atlas revealed its mysteries. Each anomaly emerged just as instruments became capable of detecting it. The CO2 emission appeared when SPHEREX could map it. The thermal plateaus emerged when Webb could measure them. The subtle tail materialized when Gemini South achieved sufficient sensitivity. It was as if the object was teaching us to observe by revealing features timed to our technological development. Dr. Paul Davies at Arizona State University identified what he termed the pedagogical progression in 3I Atlas's anomalies. Simple mysteries appeared first, unusual velocity and chemistry that challenged but didn't break existing models. Complex anomalies emerged later, thermal regulation and selective volatility that required new physics. The progression resembled a carefully designed curriculum, each lesson building on previous understanding while introducing concepts just beyond current knowledge. The selective revelation of properties suggested sophisticated information management. 3I Atlas showed enough activity to prove it contained volatiles, but not enough to determine internal structure. It displayed enough organization to suggest control, but not enough to prove artificiality. Every measurement yielded information that deepened mystery rather than resolving it. The object wasn't just anomalous. It was precisely anomalous in ways that maximized scientific engagement. Dr. Stephen Dick, former NASA chief historian, analyzed 3I Atlas through the lens of interstellar communication strategies. Any message sent between star systems faced the challenge of recipient comprehension. The sender couldn't know the exact technological level of the receiver, requiring messages that could be understood across a range of developmental stages. 3I Atlas's behavior was consistent with a probe designed to engage civilizations anywhere from early space age to advanced interstellar capability. The game theory implications were particularly unsettling. If 3I Atlas was artificial, its creators had chosen to maintain ambiguity rather than making their presence obvious. This suggested either extreme caution about revealing themselves or a test of humanity's ability to recognize subtle signs of intelligence. The burden of proof had been placed entirely on human observers, with the visitors providing just enough evidence to reward careful investigation without confirming anything definitively. Dr. Jacob Hack-Misra at the Blue Marble Space Institute calculated the statistical probability that random natural processes could produce 3I Atlas's specific pattern of anomalies. The likelihood was approximately 10 to the minus 12, essentially 0. But the alternative, accepting artificial origin, carried implications that science wasn't prepared to handle. The object had trapped humanity between statistical impossibility and philosophical impossibility. The message, if one existed, might not be in any single anomaly, but in their collective pattern. The CO2 chemistry said, "Notice me." The thermal regulation said, "I'm controlled." The perfect timing said, "This isn't coincidence." The December reappearance would potentially add new elements to this pattern, either confirming the message interpretation or revealing that humanity had been seeing patterns in cosmic static. The most disturbing possibility was that 3I Atlas represented a filter, identifying civilizations capable of recognizing subtle signs of intelligence. Those who noticed might receive further contact. Those who dismiss the anomalies as natural might be deemed unready for interaction. December's observations would potentially determine not just what 3i Atlas was, but what humanity's response revealed about our readiness to join a galactic community that communicated through calibrated ambiguity rather than obvious signals. The engineering studies for intercepting 3i Atlas revealed a harsh truth about humanity's position in the cosmic hierarchy. Despite possessing the technology to detect and track interstellar visitors, we remained fundamentally incapable of physically reaching them. The gulf between observation and interaction had never been more painfully apparent than in our frustrated attempts to design a mission to 3i Atlas. Dr. Damon Landau at JPL led the trajectory analysis team that explored every conceivable option for intercept. The fundamental problem was velocity. 3i Atlas was moving at 61 kilometers per second relative to the Sun, faster than any spacecraft humanity had ever launched. Even reaching a fraction of that velocity would require propulsion systems operating at the absolute limits of theoretical efficiency. Chemical rockets, humanity's workhorse for space exploration, were immediately ruled out. The Tsiolkovsky rocket equation showed that achieving the necessary delta V would require fuel masses exceeding the payload by factors of millions. A spacecraft the size of a car would need fuel tanks larger than supertankers. The specific impulse of chemical propulsion simply couldn't provide the energy density required for interstellar intercept. Nuclear propulsion offered better possibilities, but still fell short. Project Orion-style nuclear pulse propulsion could theoretically achieve the necessary velocities, but the engineering challenges were insurmountable on short timescales. Building and testing nuclear rockets would take decades, and international treaties prohibited nuclear explosions in space. By the time such a mission could launch, 3i Atlas would be beyond the orbit of Neptune. Dr. Les Johnson at NASA's Marshall Space Flight Center evaluated solar sail concepts for 3i Atlas intercept. A sufficiently large sail, perhaps kilometers in diameter, could use solar radiation pressure to achieve high velocities. But deployment and control of such massive structures remained beyond current capability. Even theoretical designs couldn't achieve intercept velocities in time to catch 3i Atlas before it left the solar system. The breakthrough starshot concept, using powerful lasers to accelerate tiny probes to relativistic speeds, might have worked if the infrastructure existed. But the required laser arrays, generating gigawatts of coordinated power, remained decades from construction. The technology to intercept interstellar visitors existed in theory, but not in practice, a frustrating gap between knowledge and capability. Dr. Ralph McNutt at Johns Hopkins Applied Physics Laboratory proposed the most realistic near-term option, redirecting existing spacecraft. Several missions currently traveling through the outer solar system might pass within observational range of 3i Atlas. With careful trajectory modifications, these spacecraft could potentially achieve flyby encounters, though not true intercepts. The Juno mission at Jupiter represented the best possibility. A precisely timed burn during Juno's December 2025 perijove could redirect it toward a March 2026 encounter with 3i Atlas. The spacecraft would pass within 10 million kilometers, close enough for its instruments to resolve surface features, but the maneuver would require consuming most of Juno's remaining fuel, ending its Jupiter mission for a single fleeting glimpse of the interstellar visitor. Dr. Linda Spilker at JPL calculated that even if perfect spacecraft were available immediately, the launch windows had already closed. Optimal intercept trajectories required launching when 3i Atlas was still approaching the inner solar system. By the time its anomalous nature became apparent, the visitor had passed the point where intercept was feasible. We were condemned to watch from a distance. The psychological impact of this impotence was profound. Humanity could split atoms, edit genes, and land robots on Mars, yet we couldn't reach a visitor passing through our own solar system. The technological pride that had accompanied the space age crumbled against the simple reality of orbital mechanics. We were still a species trapped in our local gravity well, capable of seeing the cosmos, but not truly exploring it. The failure to intercept 3I Atlas would catalyze new propulsion research, but the benefits would come too late for this visitor. Ion drives, fusion rockets, and exotic concepts like electromagnetic tethers might eventually provide the capability to reach future interstellar objects. But 3I Atlas would depart carrying its secrets, a reminder that detection without interaction was a special kind of cosmic torment. We could watch, wonder, and theorize, but we couldn't touch, sample, or truly understand this messenger from another star. The statistical implications of 3 interstellar visitors in 8 years had transformed from curiosity to urgent concern by December 2025. If current detection rates reflected true populations, hundreds of such objects were passing through our solar system annually. Most remained invisible to current surveys, too faint or fast to detect. But the Vera Rubin Observatory would change everything, potentially revealing that Earth existed in a cosmic shooting gallery of interstellar debris. Dr. Jelko Ivazic at the University of Washington, Rubin Observatory's construction director, outlined capabilities that dwarfed current surveys. The 8.4-meter telescope would photograph the entire visible sky every 3 nights, detecting objects 100 times fainter than current limits. Computer models suggested Rubin would discover between 10 and 70 interstellar visitors annually, transforming these rare events into routine observations. The preparation went beyond simple detection. Dr. Michelle Bannister at the University of Canterbury led development of rapid response protocols for the coming flood of discoveries. Each new interstellar object would require immediate characterization to determine observation priorities. With dozens arriving annually, the astronomical community needed automated systems for trajectory calculation, threat assessment, and observation scheduling. The European Space Agency's Comet Interceptor mission, scheduled for 2029 launch, represented humanity's first dedicated preparation for interstellar visitors. The spacecraft would wait at the Sun-Earth L2 point, ready to redirect toward targets of opportunity. When the next Oumuamua or 3I Atlas appeared, Comet Interceptor could intercept within months rather than years. The mission design acknowledged that we couldn't predict when or where visitors would arrive, only prepare to respond quickly. Dr. Karen Meach at the University of Hawaii coordinated the ground-based preparation network. Observatories worldwide were upgrading their target of opportunity programs, allowing instant redirect toward new discoveries. Spectroscopic instruments were being optimized for rapid chemical characterization. Radio telescopes were developing protocols for immediate SETI observations of new visitors. The infrastructure for studying interstellar objects was being built in real time. The data management challenges were staggering. Each interstellar visitor would generate terabytes of observations from multiple telescopes. Dr. Mario Juric at the University of Washington developed cloud-based systems for processing and distributing this data globally. Machine learning algorithms were being trained to identify anomalies that might indicate unusual properties or behaviors. The goal was to characterize new visitors within hours of discovery, not weeks. Classification schemes were evolving to accommodate the diversity already seen in just 3 visitors. The traditional categories of asteroid and comet were insufficient for objects like Oumuamua or 3I Atlas. New taxonomies based on chemistry, dynamics, and activity patterns were being developed. Dr. Sean Raymond at the Laboratoire d'Astrophysique de Bordeaux proposed classifications ranging from primitive to processed to anomalous, acknowledging that some visitors might defy natural explanation. The policy implications extended beyond science into international governance. If dozens of interstellar objects arrived annually, some might pass close enough to Earth to pose impact risks. The UN Committee on the Peaceful Uses of Outer Space was developing frameworks for managing potential threats from interstellar debris. The protocols had to balance scientific opportunity with planetary defense, ensuring that unusual visitors could be studied without compromising Earth's safety. Dr. Avi Loeb at Harvard proposed that the coming wave might include objects that forced acknowledgement of artificial origin. If even 1% of interstellar visitors showed undeniable signs of technology, Rubin would discover one every few years. Humanity needed psychological and institutional preparation for this possibility. The frameworks being developed had to accommodate not just natural debris, but potential artifacts from other civilizations. The commercial implications were already emerging. Companies were proposing missions to mine interstellar visitors for rare materials or scientific samples. Legal frameworks for claiming resources from objects that originated outside our solar system remained undefined. The coming wave of discoveries would force resolution of questions about ownership, exploitation, and preservation of interstellar objects. As December 2025 progressed and 3i Atlas prepared for its final observable phase, the astronomical community was simultaneously studying one visitor while preparing for hundreds more. The infrastructure, protocols, and psychological frameworks being developed would determine how humanity handled the transition from cosmic isolation to regular interaction with material from other star systems. The next wave was coming whether we were ready or not. The true terror of 3i Atlas wasn't in any single anomaly or impossible measurement. It was in the fundamental shift in how humanity understood its relationship with the cosmos. By December 2025, as the visitor prepared to vanish into interstellar darkness forever, scientists confronted a reality that would haunt them long after 3i Atlas became undetectable. The universe was not what we thought it was. Dr. Martin Rees, Britain's Astronomer Royal, articulated what many scientists felt but couldn't publicly express. The universe revealed by 3i Atlas wasn't empty and indifferent, but populated and possibly attentive. Every assumption about cosmic isolation that had shaped human thought for millennia was crumbling. We weren't alone, and more disturbingly, we might be under observation by intelligences whose capabilities and intentions remained utterly opaque. The psychological surveys conducted by Dr. Susan Chen at Stanford revealed profound changes in how people related to the night sky. Before 3i Atlas, stars were distant lights, beautiful but irrelevant to daily existence. Now they were potential homes to civilizations that might be sending probes through our solar system. The cosmos had transformed from backdrop to active participant in human affairs. People reported difficulty sleeping, not from fear, but from a kind of cosmic vertigo. The Drake equation, which estimated the probability of extraterrestrial civilizations, required fundamental revision. If interstellar visitors like 3i Atlas were artificial, then technological civilizations weren't rare, but common enough to fill the galaxy with their debris or probes. Dr. Seth Shostak at SETI calculated that explaining 3i Atlas's properties through natural processes required coincidences so improbable that artificial origin became the more conservative hypothesis. Religious institutions struggled with implications that challenged core theological assumptions. If 3i Atlas was artificial, it suggested civilizations that had achieved technological immortality, surviving billions of years. What did salvation mean for beings that had conquered death? How did Earth's religions apply to consciousnesses that might be artificial, collective, or fundamentally non-biological? Seminary debates that had been theoretical became urgently practical. The temporal perspective was particularly unsettling. 3i Atlas had potentially been traveling since before Earth formed. When it began its journey, the universe was fundamentally different, younger, more violent, with different chemical abundances. The visitor connected us to cosmic deep time in ways that made human history seem like a fleeting biological accident. Our entire civilization was just noise in the visitor's billion-year journey. Dr. Nick Bostrom at Oxford's Future of Humanity Institute identified what he called the competence gap terror. If 3i Atlas was artificial, its creators had solved problems that might be fundamentally beyond human capability. Surviving interstellar journey for billions of years required mastery of physics, engineering, and possibly biology that exceeded human achievement by margins that couldn't be measured. We weren't just behind, we might be categorically inferior. The selective revelation of information by 3i Atlas suggested even more disturbing possibilities. If the object was artificial and deliberately maintaining ambiguity, it implied intelligences that understood human psychology well enough to calibrate their revelations precisely. They knew exactly how much mystery we could tolerate, how much evidence we needed to stay engaged without achieving certainty. We weren't just being observed, we were being manipulated by minds that understood us better than we understood ourselves. The silence of the galaxy took on new meaning in light of 3i Atlas. Perhaps civilizations weren't broadcasting because they communicated through directed probes. Perhaps they maintained silence while sending observers to evaluate younger civilizations. The Great Silence might not indicate absence, but presence. Civilizations advanced enough to observe without being observed, to study without being studied. As December ended and 3i Atlas faded beyond detection, humanity was left with a transformed cosmos. The universe was no longer empty, but potentially crowded with intelligences whose probes or debris regularly passed through our solar system. We couldn't return to the comfortable assumption of cosmic solitude. Every future observation would be shadowed by the possibility that we were seeing not just natural phenomena, but the activities of civilizations whose purposes remained incomprehensible. The final terror was the certainty that more visitors would come. The universe that had delivered 3i Atlas would send other messengers, each potentially stranger than the last. Humanity would spend the coming decades watching the skies with new eyes, understanding that the cosmos wasn't just watching back but might be actively engaged in ways we were only beginning to perceive. The cosmic perspective had shifted permanently, and with it, humanity's understanding of its place in a universe far stranger and more populated